Each year, the U.S. livestock industry alone generates $300 billion in revenue, roughly equivalent to the entire GDP of the Czech Republic, one of Europe's leading industrial hubs. But how can a country where less than 1% of the population works directly in agriculture manage more than 10 billion animals, transforming livestock farming into such a precise and highly efficient industry? In this video, Agriculture Insight explores 5 major livestock strongholds of the United States, where large-scale production models emerged from waves of migration, accelerated by the Transcontinental Railroad, and were shaped by the descendants of the Wild West cowboys. From small, handcrafted farms, everything has evolved into a tightly controlled system, monitored at every stage of production. Our first stop takes us to Georgia, the largest state east of the Mississippi River, characterized by the hot, humid subtropical climate typical of the American South. These natural conditions, harsh for humans, have ironically become the perfect foundation for Georgia to build a vast poultry empire, earning it the title of the poultry capital of the world. In the 1920s, when the boll weevil infestation wiped out cotton fields across the region, local farmers pivoted to chicken farming, repurposing the existing railroad network to ship food into massive consumer markets such as Chicago and New York. Today, Georgia's poultry industry operates under an extremely strict, vertically integrated model, where corporations like Cobb Vantress engineer super chickens, with reinforced leg bone structures and resilient cardiovascular systems, capable of supporting body weights that double in half the time compared to previous generations. Inside high-tech poultry houses, LED lighting is dimmed to minimal levels to suppress movement, forcing energy to be almost entirely channeled into developing breast meat, the most economically valuable cut of white meat. This precision-controlled system allows chickens to reach market weight in just 6 to 7 weeks, achieving optimal feed conversion ratios and sustaining an average annual consumption of 46 kilograms of chicken per American. Beyond domestic supply, nearly 1/4 of Georgia's poultry output is exported worldwide. Mexico remains the largest market, followed by massive shipments of chicken feet to China and low-cost drumstick exports flowing into Southeast Asia. Through this fully closed-loop production system, the poultry industry generates over $4 billion annually, transforming Georgia into an irreplaceable node within the global food security chain. Leaving the hot, humid South behind, we arrive in the frozen Midwest of Minnesota, the leading turkey-producing state in the United States, with more than 40 million birds sent to market each year. The industry here operates on an exceptionally tight logistics system, where massive hatcheries and feed mills are built directly adjacent to farm clusters, eliminating transportation costs and minimizing the risk of supply chain disruptions during the region's brutal winters. This level of control allows Minnesota farmers to raise highly specialized turkey breeds, selectively engineered to concentrate the vast majority of body mass into the breast. However, this extreme growth rate comes at a biological cost. The birds become physically incapable of natural mating, forcing specialists to rely on 100% manual artificial insemination to sustain production. If turkeys are not slaughtered within the strict window of 18 to 20 weeks, their cardiovascular systems will collapse under the weight of muscle mass that far exceeds that of naturally grown birds. To withstand temperatures plunging to 20 degrees Celsius, poultry houses are designed like fully insulated bunkers, operated with negative pressure ventilation systems to control ammonia levels from waste, preventing eye blindness and respiratory burns in the flock. While turkey breast meat is retained domestically to supply America's deep processing food chains, more than 60% of exported thighs and wings are shipped to Mexico. Minnesota also dominates a high-margin niche market by exporting gizzards and internal organs to Europe as raw material for premium pâtés, generating profit margins far beyond conventional meat cuts. This positioning transforms the state into a strategic node, controlling the flow of poultry protein across Latin America and parts of the European Union. Our next stop takes us to California's Central Valley, a region known not only for oranges and wine, but also as the headquarters of the largest dairy industry in the United States, home to more than 1.7 million dairy cows. To sustain nearly 20% of the nation's total milk output, farms here operate under a single overriding priority: surviving an increasingly hostile natural environment. Annual rainfall in the valley falls below 300 millimeters, turning water into a luxury commodity. Dairy operations are forced to compete directly with almond orchards for water rights, with prices swinging as violently as stock markets during peak drought periods. As groundwater reserves are depleted, water is pushed into a fully closed-loop reuse system. It begins with continuous misting systems designed to prevent heat stress and sudden death in cattle, then flows into floor cleaning operations before being redirected straight into irrigation for feed crop fields. This drive for efficiency extends into precision total mixtration (TMR) feeding, where rations are software calculated to maintain productivity even under severe heat stress. Instead of relying solely on fresh forage, which demands enormous volumes of irrigation water, California dairy cows consume millions of tons of almond hulls and grape pomace sourced from neighboring valleys, transforming agricultural waste into low-cost protein inputs. At the same time, milking operations are fully industrialized through rotary milking systems capable of processing thousands of cows per hour. Each animal wears sensor-equipped collars that track behavior and health in real time, turning every cow into a living data point. This allows farm managers to make predictive, data-driven decisions, from optimizing breeding cycles to detecting disease early, rather than relying on instinct. Powered by this technological foundation, California has become a massive supplier of raw milk for the global milk powder industry, while also dominating the mozzarella cheese segment that feeds international fast food chains. Yet this prosperity faces a critical bottleneck: labor. Up to 90% of the workforce on dairy farms consists of immigrants, primarily from Mexico and Central America. As border policies tighten and the cost of living in California continues to rise, the dairy sector is struggling to maintain the round-the-clock labor required to keep operations running. To offset rising costs, farm owners are increasingly investing in anaerobic digesters, converting manure into renewable natural gas sold back into the state's energy grid. This shift creates a secondary revenue stream that helps preserve profitability, but it also pushes smaller farms toward bankruptcy due to the high capital costs of technology adoption. As a result, power within the dairy industry is becoming ever more concentrated in the hands of a few mega-corporations that now control both food production and energy generation. In Iowa, pigs now outnumber people by a ratio of 8-to-1. With a total herd exceeding 24 million head, the majority of pork produced in the state supplies the domestic U.S. market, while also serving strategic export destinations such as Mexico, Japan, and especially China. To enter a mega operation like Iowa Select Farms, visitors must comply with an uncompromising biosecurity protocol, removing personal clothing and undergoing full decontamination showers. All infection risks are eliminated at the gate because once disease breaches the system, economic losses are measured in millions of dollars per day. Inside, each barn functions with the precision of a modern medical laboratory. To maximize productivity, the production system is divided into strictly separated zones. In breeding units, Sows are housed in metal gestation stalls, designed to optimize artificial insemination while allowing precise digital tracking of each individual. In farrowing units, specialized protective crates are used, mechanical designs that prevent the sow's natural movements from crushing piglets, ensuring near-total survival rates and guaranteed access to colostrum. All waste is managed through slatted flooring systems, keeping the environment dry while physically separating animals from pathogens. This level of precision allows a single facility with 3,000 breeding sows to consistently supply 1,300 piglets per week to satellite finishing farms. Notably, Iowa has completely eliminated antibiotic growth promoters to meet the strict standards of premium markets such as Japan, limiting antibiotic use solely to therapeutic treatment under veterinary supervision. This approach not only addresses animal welfare concerns, but also serves as a passport for Iowa pork to enter the world's most demanding supply chains. Beyond animal husbandry, the most valuable asset of Iowa's model lies in its closed-loop resource cycle. The massive volume of manure generated by hog farms is converted into organic fertilizer for local cornfields. That corn, in turn, flows back into feed rations for the pigs, eliminating intermediary transport costs entirely. At larger operations, methane capture technology goes one step further, converting livestock waste into electricity that feeds the local power grid, pushing the model of circular agriculture to its next evolutionary stage. Everything in Texas is bigger, and its herd of 12 million cattle is the clearest proof. For comparison, that number exceeds the combined populations of Greece and Norway. With grazing land accounting for nearly 1/4 of all livestock acreage in the United States, Texas is not only the nation's largest beef-producing state, but also a primary supplier to Mexico via land border crossings. Many people assume longhorns are the backbone of Texas ranching. In reality, Black Angus and heat-tolerant crossbreeds like Brangus are the true economic workhorses. In the early stages, cattle roam freely across ranches spanning thousands of acres, developing strong natural skeletal frames. Once they enter the finishing phase, they are moved into massive feedlots, where they are fed energy-dense diets of cracked corn and cotton byproducts. The objective is clear: reach 600 kilograms live weight with commercially viable marbling. The greatest challenge facing Texas cattle production, however, is extreme weather. A cow with a thick coat can tolerate temperatures as low as 8 degrees Celsius thanks to natural insulating air pockets trapped between coarse hair fibers. But the real enemy is freezing rain and snow. Once soaked, the coat collapses and freezes directly against the skin, eliminating insulation entirely. At that point, the animal must burn its entire energy reserve simply to survive, resulting in rapid weight loss, a worst-case economic scenario for any rancher. To solve this problem, Texas has transformed bushland, one of the world's densest cattle feedlot regions, into a center for digitized livestock management. At the Texas A&M AgriLife Research Center, drones are gradually replacing traditional cowboys. Instead of manual inspections, specialists deploy thermal imaging cameras to scan thousands of animals, accurately identifying individuals with elevated body temperatures during the earliest incubation stages of disease. This enables targeted treatment, reducing costs while preserving meat quality and minimizing unnecessary intervention. After roughly 150 days of finishing, cattle that meet specifications are transported directly to large-scale packing plants operated by JBS or Tyson Foods, located within the state. There, AI-assisted grading systems, alongside USDA inspectors, classify beef based on marbling levels. Yet despite meticulous care, only about 5% of total output qualifies as USDA Prime, the highest grade destined for elite steakhouse markets worldwide. Beyond Mexico, demanding markets such as Japan and South Korea have become core buyers of Texas beef, accounting for up to 60% of export value, driven by trust in the strict production standards of this modern Western cattle empire. Most agricultural powerhouses possess at least one of two fundamental advantages: vast land area or a favorable climate. But for the Netherlands, their starting point consisted largely of land lying below sea level. Without expansive alluvial plains like those of France or Germany, most of their territory is made up of polders, artificial lands sustained by dike systems and pumps operating 24/7. Here, agricultural production constantly confronts saltwater intrusion, high humidity, and a lack of natural sunlight. It was precisely these harsh physical constraints that forced the Netherlands to choose a different strategy. Instead of expanding agriculture horizontally, like the United States or Russia, they focused on optimizing value density per unit of land area. At this point, every scarce square meter had to operate at extreme intensity, and even be completely detached from the soil. All of the most remarkable agricultural achievements begin with seeds. And in the Netherlands, more than 200 breeding companies have transformed the country into the world's leading hub of seed technology. Here, seeds are not developed for mass production, but are engineered as a core technical component specifically for smart greenhouses. They possess inherent disease resistance and respond precisely to every milligram of nutrients in a controlled cultivation environment. If the United States has Silicon Valley for software, then the Netherlands has Seed Valley, a hub that brings together more than 40 seed corporations, closely connected with Wageningen University and the government, enabling new plant varieties to move from the laboratory to global production in just a few years. You may be astonished to learn that 1 kilogram of specialized tomato seeds here can cost up to 50,000 USDs, as expensive as pure gold. This extraordinary price reflects billions of dollars invested in genetic research, allowing crops to achieve maximum yields while maintaining strong resilience without the need for chemical plant protection products. With this capability, the Netherlands now controls 25% of the global vegetable export value and 60% of the global seed potato market. From the United States to China, many of the world's leading agricultural systems are directly dependent on plant varieties originating from this low-lying land. Alongside seeds worth billions of dollars, another revolution in cultivation environments was pioneered, standardized, and spread worldwide by the Netherlands: Rockwool growing media. At first glance, they appear to be nothing more than soft, lifeless foam blocks. But Rockwool is in fact a complete replacement for the role of soil, a survival breakthrough for countries where arable land is always a luxury. The foundation of this technology comes from basalt rock and ores melted at 2700 degrees Fahrenheit. From this glowing stream of molten material, the lava is spun centrifugally into ultrafine mineral fibers and compressed into solid blocks. Thanks to its volcanic mineral origin, its superiority lies in its chemical inertness and absolute sterility, creating an almost perfectly clean biological growing medium that completely eliminates pathogens and prevents the nutrient losses commonly seen in traditional soil-based cultivation. Complete separation from soil gives Dutch engineers ultimate control. They precisely program nutrient concentrations and pH levels down to the milligram, delivering them directly to the root system without any interference or loss caused by impurities or unwanted absorption. From there, Rockwool's fiber structure creates an ideal paradox for plants. It can retain water many times its own weight while still maintaining ultra-fine air pockets. This ensures roots are constantly supplied with maximum oxygen, completely eliminating the risk of waterlogging and common root diseases. Today, this technology covers more than 80% of greenhouse area in the Netherlands. Each growing block is a critical node in a closed-loop circulation system, directly connected to a central computer. The result is astonishing efficiency, up to 90% water savings and 40% fertilizer savings. And it doesn't stop there. All excess water is collected, sterilized, and reused, turning greenhouses into a sustainable production cycle that achieves the highest yields on the planet. When the Netherlands is mentioned, the whole world immediately thinks of vibrant tulip fields. But on the agricultural map, this is not a center for commercial flower production. It is home to the world's largest tulip bulb production facilities, supplying up to 2.5 billion bulbs globally each year. These bulbs form the foundation of the entire global flower supply chain, especially for massive markets such as the United States. However, to maintain this record-breaking position, Dutch farmers must carry out a decisive process, completely removing the flowers at their peak bloom. A tulip bulb requires 5 to 7 years of care before it is able to bloom. But the moment the petals reach peak color maturity, specialized flower removal machines are deployed immediately to redirect the plant's nutrient flow. Designed with rotating shafts integrated with rubber paddles and cutting blades, the core mechanism of these machines focuses force on the plant's weakest point, just beneath the flower head. As the machine moves forward, the high-speed rotating shaft snaps or cleanly cuts off the flower head without damaging the leaves or stem. Removing the flower head immediately halts seed formation and energy consumption at the top of the plant. This forces all sugars and minerals produced through photosynthesis to be redirected downward, concentrating nourishment into the bulb. By summer, when the leaves have withered, about 2 months after the flowers are removed, the true industrial harvesting process begins. Steel cutting systems lift the entire soil layer at a depth of around 20 centimeters, feeding it onto vibrating conveyor belts that sift and separate the bulbs on site, processing hectares of land each day. The breakthrough lies in crop protection. Despite being industrial machinery, all conveyors are lined with rubber padding and use high-pressure air-blowing systems to protect the thin, sensitive outer skin. This airflow not only removes dirt and fine sand, but also ensures the bulbs are not scratched, crucial for preventing bacterial infiltration during export. As a result, Dutch tulip bulbs grow to 10 to 12 centimeters in size, the gold standard for replanting in the world's most demanding markets. But make no mistake, beyond its empire of bulb production in open fields, the Netherlands still maintains a leading position in professional cut flower production within high-tech greenhouses. After being harvested by automated conveyor systems, millions of flower stems are consolidated and transported to Royal Flora Holland, the largest flower auction in the world. Transportation operates continuously via electric carts moving through an extensive system of sorting warehouses. Each day, this exchange offers up to 20,000 different types of flowers and ornamental plants. For tulips alone, prices fluctuate by the second and by season, but are typically successfully auctioned at an average range of $0.22 to $0.55 per stem. While other countries require several days for transshipment, the Dutch reverse auction model delivers absolute price transparency and extremely fast capital turnover. Although the Netherlands is not the world's largest consumer market for fresh flowers, it functions as the brain that regulates global supply, allowing tulip shipments leaving the auction floor to land in the United States or Japan within just 24 hours after a deal is closed. With only 1.5 million cows, just 1/6 the scale of California, the Netherlands still amazes the world with record-breaking productivity. More than 9,000 kilograms of milk per cow per year. Each cow is a data node within a farm-wide IoT network. Through smart chips, the system can analyze and predict health risks up to 48 hours before clinical symptoms appear. This level of precision eliminates nearly all random variables, turning farms into an ideally optimized ecosystem. But in the Netherlands, technology doesn't exist only on charts. It takes physical form through tireless field operating machines, Lely robots. In reality, the number of farms in the Netherlands is declining by nearly 3% each year due to environmental pressure and a lack of successors, yet herd sizes continue to grow. Faced with this challenge, an automation revolution became inevitable, and at its center is the Lely Vector robot. Its crane system uses sensors to locate and precisely grasp roughage with a deviation of less than 2%. Immediately afterward, automated pipelines inject exact amounts of concentrated feed, which are mixed by an auger into a uniform blend, ensuring cows absorb nutrients completely and eliminating selective feeding. After mixing, the robot autonomously navigates through the farm to distribute feed. Its smartest feature lies in the ultrasonic sensors. The system measures the height of leftover feed and dispenses more only when necessary, ensuring troughs remain full while maintaining freshness 24/7. Notably, a single system consumes only about 20 kilowatt-hours per day to care for hundreds of cows. This quiet operation, with extremely low energy use, not only replaces human labor, but also creates a perfectly calm environment, key to keeping cows relaxed, maximizing oxytocin release, and sustaining peak milk productivity. To maintain high productivity, every cow needs a continuous energy intake. However, cows tend to use their noses to push feed sideways and out of reach, causing feed to scatter and go to waste. Lely Juno is designed to solve this problem. The robot operates as an automated system that moves along feed alleys 24/7, gathering and pushing feed back toward the fence. Keeping feed constantly within reach not only minimizes waste, but also stimulates cows' natural feeding behavior. Real-world results show that Lely Juno increases dry matter intake by 3%, equivalent to nearly 1 additional kilogram of milk per cow per day, simply by optimizing how feed is delivered. In the past, milking was the most exhausting burden for farmers. They had to wake up at 4 to 5 a.m., manually operating equipment for hundreds of cows on a forced schedule. This process not only drained human energy, but also placed significant stress on the herd. The Lely astronaut robot completely changed the game with a voluntary principle. Cows independently choose to be milked whenever they want, averaging 2.5 to 3 times per day. As soon as a cow enters position, the system scans its smart tag to retrieve health records and dispenses the exact amount of concentrated feed tailored to that individual. Notably, the robot is capable of real-time quality control. Sensors continuously analyze parameters ranging from electrical conductivity and fat content to somatic cell counts. At the slightest sign of mastitis or any indicator falling outside standards, a diversion valve immediately redirects the compromised milk into a separate tank without any human intervention. At the end of the process, the milking cups automatically detach and retract to a standby position, never touching the floor to ensure hygiene. The milk that meets standards then flows directly through a rapid cooling system to below 4 degrees Celsius before entering the main refrigerated storage tank. This entire journey takes place in a closed system, preventing any contact with air or bacteria. Beyond boosting milk yield by an additional 15%, this robot redefines livestock farming as a smart production line, where humans manage data while cows are free to live according to their natural biological rhythms. Beyond Meat targeted consumers who still enjoy eating meat, with burgers made from pea protein, promising to reduce dependence on animal farming without forcing people to change their eating habits. Meanwhile, Impossible Foods chose a faster and broader path, partnering with Burger King. The Impossible Whopper, made with soy protein, generated over $100 million in just 4 months, becoming one of the most successful product launches in the history of American fast food. But the excitement did not last long. Shortly after Beyond Meat reached a peak market capitalization of nearly $14 billion USD, the US plant-based meat market began to stall and then decline. Consumers shifted from curiosity to skepticism. Despite having protein levels comparable to beef, plant-based meat is a highly processed product, often containing high sodium levels and an ever-growing list of ingredients. The paradox lies here. In supermarkets, a single Beyond Burger still costs more than $2 nearly twice the price of a standard frozen beef burger. So what exactly in the production process has driven the cost of plant-based meat to this level? And who is really paying that price? For technology, for the environment, or for consumer expectations themselves? The journey of plant-based meat, often described as a solution to reduce the environmental burden on the planet, actually begins with something remarkably small: soybeans. From late September through November, soybean fields stretching across the American Midwest enter peak harvest season. More than 70% of today's plant-based meat products rely on soybeans, not by chance, but because of their exceptional water-holding capacity and fiber-binding properties, which create the closest chew and fibrous pull to real meat. To preserve these characteristics, soybeans must be harvested at a precise biological window. The plant has dried, while the beans retain approximately 15% moisture. Harvest too early, and the proteins are not yet stable. Harvest too late, and the beans crack easily, losing their ability to bind and form structure. When harvesting begins, headers nearly 12 meters wide are lowered close to the ground to collect pods growing low near the base of the plant, where nearly all yield is concentrated. Inside the machine, threshing drums, sieve systems, and air fans separate the pods while keeping the beans intact. Meanwhile, dry stems and leaves are returned to the field, forming a biological mulch layer that protects the rich mollisol soils beneath. Each hectare can yield around 4 tons of soybeans, but for the plant protein industry, only batches with at least 95% intact beans are accepted. Cracked beans, though still edible, have lost their ability to form fibers and gels, making them unsuitable for replicating the structure of real muscle tissue. These stringent requirements mean that the plant protein supply chain cannot rely on a single crop alone. To create a light-colored protein base with a neutral aroma and lower allergenic potential, the industry also turns to peas. Unlike soybeans, peas used for protein extraction are harvested while the plants are still green, when the seeds have reached full size but before starch conversion begins. This requires an entirely different type of machinery, the pea viner, a machine designed to separate fresh peas rather than cut and thresh dried crops like conventional harvesters. At the front, gathering reels pull in the entire plant and feed it directly into the machine. An in-feed elevator lifts the full vines into the separation chamber, where high-speed but low-impact beaters open the pods, allowing the peas to fall free without being crushed. The material stream then passes through a rotating screening drum, continuously sorting between acceptable peas and remaining plant matter. Clean peas are transferred into a sealed onboard hopper, preventing contamination and minimizing mechanical damage during transport. Operating in a continuous cycle, each pea viner can process approximately 3 hectares per hour, supplying a steady stream of raw material to protein isolation facilities. From this moment onward, the quality of plant-based meat is already determined in the field, long before any downstream technology intervenes. The process begins by blending plant proteins with liquid fats. Isolated and dried legume proteins are fed into sealed mixing vessels, where they are combined with water, vegetable oils, and emulsifiers to recreate the fat content and water-holding capacity of meat. Within minutes, the proteins become fully hydrated, forming a moist, pliable mass. Under high torque, protein chains are forced to realign in the same direction, creating fibrous structures that produce the tear and chew associated with meat. Among them, soy protein provides more stable chewiness, while pea protein offers a milder aroma but a softer structure. However, texture alone is not enough. To generate aroma and flavor during cooking, leg hemoglobin, a heme source naturally found in legume root nodules, is fermented, filtered, and concentrated into a dark red solution, then added to the protein matrix. This compound triggers the Maillard reaction, producing savory aromas, umami flavor, and a brown seared crust when exposed to heat, while beet-derived pigments serve only to enhance the red color in the raw state. Once the meat matrix reaches sufficient plasticity and cohesion, the entire mixture is fed directly into an automated forming system. The soft mass is continuously extruded and precisely cut to preset dimensions, ensuring that every piece leaving the machine is identical in thickness and structure. Round shapes are used for burgers as they fit perfectly with sandwich buns. Rectangular forms are chosen for sandwich patties and ready-to-eat meals, thanks to their ease of stacking and precise portion control on industrial production lines. Immediately afterward, each patty is automatically placed into trays, sealed, chilled, and packed into cartons. From this point on, plant-based meat becomes a fully standardized product, ready for global distribution by manufacturers in the United States and Europe. On a separate production line, raw plant-based meat is also fed into structure testing and compression forming systems. Pressure and compression forces are carefully calibrated to replicate the thickness, elasticity, and cooked state behavior of real beef burgers before packaging. Once taken off supermarket shelves, plant-based meat is cooked almost exactly like traditional ground meat, but in reality, it is far easier to control during cooking. Anyone can become a home cook with a single pack of plant-based meat pulled from the refrigerator. Because the proteins have already been processed and stabilized in the factory, the mixture shrinks less, retains moisture better, and does not require precise timing for rare or medium doneness. This makes it especially well suited for quick pan searing and burger forming. With just 2 to 3 minutes of direct contact with a hot pan, the patty rapidly develops a brown crust and familiar savory aroma, while the interior remains evenly moist. For many American households, this is a clear advantage. Pre-packaged plant-based meat delivers consistent results, even when the cook has limited time or experience. At a professional scale, this advantage becomes even more pronounced. In fast casual chains, modern burger restaurants, and experimental kitchens run by young chefs, plant-based meat is often treated as a neutral protein base, lightly seasoned, pan-seared, or pressed flat to fine-tune bite texture. Thanks to its uniform structure, each batch produces nearly identical size, doneness, and cooking time, allowing restaurants to operate smoothly even during peak hours. Notably, frozen plant-based meat typically has a shelf life of 6 to 9 months, giving restaurants far greater inventory flexibility and significantly reduced waste compared to fresh meat. We rarely stop to think about this, but the number of livestock animals now exceeds the human population by 4 times, and the total biomass of animals raised for meat is nearly 10 times greater than that of all wild mammals combined. From an environmental perspective, industrial livestock farming accounts for around 14% of global greenhouse gas emissions. roughly equal to or even slightly higher than the entire transportation sector. In other words, in terms of emissions, the piece of beef on your plate carries a greenhouse footprint comparable to that of a vast transportation system operating every day. A spinach crop takes about 6 to 8 weeks to reach its golden harvest moment. Across the vast fields of California, which produces more than 70% of America's spinach, you'll see cut and convey harvesters moving swiftly like mobile production lines across the land. What's impressive about this system is its cutting deck, spanning over 4 meters wide, capable of slicing through 3 rows at once, and even adjustable to match different row spacings. As soon as the blades grip and lift the leaves from the soil, a closed-loop process of cutting, collecting, conveying, and loading begins instantly, minimizing bruising and keeping the spinach clean, cool, and intact from the very moment it leaves the ground. For delicate leafy greens like spinach, which can deteriorate within just a few hours, this machine provides almost every advantage needed to preserve crop quality before entering the processing area. However, if you're running a farm in areas with high humidity, poor drainage, and frequent rainfall, you might want to consider using a fan suction harvester, a true weapon for wet fields. With a cutting width of just over 3 meters, it's much more compact than the conveyor-type machines. Thanks to its lift-first, cut-later mechanism, the machine uses a powerful fan to raise the leaves before the blades make contact, reducing up to 40% of mud buildup, a problem that often troubles other harvesters when dealing with soft, wet, and sticky leaves. That said, this system consumes more fuel and requires constant adjustment of suction power, which is why many large farms prefer to combine both technologies, staying flexible and ready for any weather conditions. At the peak of the winter season, up to 12 tons of leeks are processed every hour, thanks to mechanization. This is achieved with clamping belt harvesters, machines specifically designed for tall cylindrical crops, operating through a seamless sequence of lifting, clamping, pulling, cutting, and collecting, all in a single motion. The structure of this machine is remarkably sophisticated. The undercutter blade slides up to 15 centimeters beneath the soil to sever the roots without breaking the stalk. Immediately afterward, 2 hydraulic belts grip each plant firmly and pull it upward at a steady speed. Along the body of the harvester, a rotating blade assembly trims away the excess leaves before a conveyor belt carries the cleaned leeks into storage bins ready for sorting. Today, the efficiency of mechanization goes beyond just saving labor. It's about eliminating environmental risks, from biting winds and muddy fields to unpredictable planting schedules dictated by the weather. Once the pace of harvest is no longer imprisoned by winter, leeks can be collected more evenly, ensuring a steady supply regardless of the cold. There are many ways to harvest honey, but the most common method involves honeycomb frames and an extractor machine. Before the process begins, beekeepers borrow some smoke to communicate with the bees. Not to drive them away, but to trick their survival instinct. The bees believe there's a forest fire, so they focus on gorging on honey and temporarily stop sending attack signals. Once at the hive, each honey-filled frame is carefully lifted out, where the golden wax caps signal that the honey is ripe, with an ideal moisture level of about 18%. After the wax caps are removed, the frames are placed inside a centrifugal extractor. There, the spinning motion flings the honey out of the hexagonal cells without damaging their structure. A biological masterpiece that the bees can reuse almost completely for the next season. Thanks to this delicate process, a healthy colony can produce 2 to 4 harvests per year, without exhausting the bees. Beyond honey harvesting, have you ever been fascinated by any other kind of manual harvest? For me, one of the most mesmerizing sights is watching a skilled tapper carve precise, elegant lines into the bark of a rubber tree to collect its milky sap. This work usually begins before dawn, the time when the latex flows thickest and stays fluid longer thanks to the cool temperature. The sap naturally runs from upper right to lower left, so the tapper must angle the blade at about 45 degrees to optimize the flow. Immediately afterward, a plastic spout is secured with wire at a 30-degree tilt to guide the latex into a small cup. Each cup is only about the size of a palm, so workers must check them frequently to prevent overflow or contamination from rainwater, which could cause the sap to coagulate early, become impure, and lose commercial value. This entire process is a blend of technique, experience, and delicate precision. And perhaps because of that, even today, around 90% of the world's natural rubber is still harvested by hand, preserving the timeless image of dedicated workers tapping rubber trees across vast tropical plantations. The acai berry clusters, hanging high on palm trees that reach 60 to 80 feet, are both a lifeline and a peril for countless working families in Brazil. Throughout the long harvest season, stretching deep into winter, the pickers, known as pecaneiros, must climb the slick, narrow trunks using nothing but a rope looped around their ankles for grip as they scale all the way to the crown. Studies show that over 90% of harvesters have suffered injuries, ranging from sprains and fractures to serious trauma caused by slips and falls. Yet when the berries turn a deep purple, with just the right shine and elasticity, they still climb and cut each fruit cluster with a knife, then carry it pressed against their bodies on the way down. Each bunch can weigh up to 6 kilograms, but only 10 to 15% of that weight is usable pulp for processing. A painstaking price for the exhausting labor repeated dozens of times each day. Year after year, acai harvesting remains one of the great paradoxes of the Amazon. A fruit that depends entirely on human strength and skill, yet fuels one of the fastest growing superfood markets in the world. Before you is the Pickrite HC290, a machine that quite literally devours tomatoes, capable of processing up to 80 tons per hour across vast fields, ripening all at once. The highlight of this harvester lies in its dual forced balance shaker system, which gently but efficiently shakes each tomato free from the vines with remarkable speed and uniformity. Immediately after, the vines are fed into a chopper, shredded, and returned to the field as organic matter, while the tomatoes move through fans and sieves that remove soil, leaves, and other debris. Next, two 48-inch electronic color sorters identify and reject green or damaged fruit, keeping only those that are fully or nearly red, before transferring them directly into trailers running alongside the harvester, all without ever stopping the machine. But now, I want to take you to a different realm of tomato harvesting, where farmers inside greenhouses spring into action the moment each cluster turns a brilliant red. Here, the true value of the tomatoes lies in the hands of the pickers. With just a gentle touch, they must feel the elasticity of the fruit to gauge ripeness, then make a precise snip at the fruit's natural breaking point on the stem, swift and clean without bruising the flesh. This delicate hand-picking technique demands extreme precision and care, because even a slight misclip or an over-twist of the shears can snap the stem, scratch the skin, or worse, send the entire cluster tumbling to the ground before it ever reaches the tray. To reduce the risks of human subjectivity, many greenhouses in the US now use tomato picking robots, assistants capable of automatically adjusting their gripping distance. The system works on a lock, grip, cut mechanism. The robot 3D scans each cluster, calculates its curvature, then lowers a Teflon-coated steel blade at a 35-degree angle to detach the whole bunch without twisting or bruising the fruit. Although costly and slower than humans, these robots offer near-perfect precision, making them especially effective for thin-skinned varieties like cherry tomatoes.